Lesson: Natural Language Processing Basics. Natural language processing represents one of the most transformative advancements within artificial intelligence, particularly when scrutinizing its potential for enhancing cybersecurity. NLP is a subfield of AI that focuses on the interaction between computers and humans through natural language. It aims to read, decipher, understand, and make sense of the human languages in a valuable way. The fundamental theories of AI, especially in NLP, offer robust frameworks that can be leveraged to fortify cybersecurity measures by analyzing vast amounts of data for potential threats, enabling more advanced threat detection and automating responses to cyber incidents. NLP's roots can be traced back to the 1950s with the inception of computational linguistics. Since then, it has evolved significantly, driven by the development of machine learning algorithms and the exponential growth of digital data. The core of NLP involves several key tasks: tokenization, part-of-speech tagging, named entity recognition, sentiment analysis, machine translation, and more. These tasks require sophisticated algorithms capable of processing natural language data accurately and efficiently. Tokenization is the process of breaking down a text into smaller units, such as words or phrases. It is a critical first step in NLP, as it sets the foundation for further analysis. Part-of-speech tagging follows, which involves labeling each token with its corresponding part of speech, such as nouns, verbs, adjectives, etc. Named entity recognition is another crucial task, where the algorithm identifies and classifies entities mentioned in the text into predefined categories like names of persons, organizations, locations, etc. Sentiment analysis aims to determine the underlying sentiment or emotional tone of the text, which is particularly useful in monitoring social media for potential cybersecurity threats. Machine translation, one of the most complex NLP tasks, involves translating text from one language to another while preserving its meaning and context. The development and application of NLP are underpinned by several theoretical models. One of the foundational models is the bag of words approach, which represents text as an unordered collection of words, disregarding grammar and word order, but keeping multiplicity. Despite its simplicity, the BOBU model has proven effective in various NLP applications, including text classification and information retrieval. However, it has limitations, such as ignoring word context and semantics. To address these limitations, more advanced models like word embeddings have been developed. Word embeddings map words into high-dimensional vectors based on their context within a corpus, capturing semantic relationships between words. Popular algorithms for generating word embeddings include Word2Vec and Glove. Word2Vec, developed by Google, uses shallow neural networks to learn word associations from large datasets, resulting in vector representations where similar words are positioned closer together in the vector space. Glove, or Global Vectors for Word Representation, developed by Stanford, combines the benefits of global matrix factorization and local context window methods to produce word vectors that capture both global statistical information and local context. The advent of deep learning has further propelled the capabilities of NLP. Recurrent neural networks, particularly long short-term memory networks, have shown remarkable success in handling sequential data and capturing long-range dependencies in text. LSTMs address the vanishing gradient problem encountered in traditional RNNs, allowing them to retain information over longer sequences. More recently, the introduction of transformer models has revolutionized NLP. Transformers leverage self-attention mechanisms to process text in parallel, significantly improving computational efficiency and performance on various NLP tasks. The bidirectional encoder representations from Transformers model, developed by Google, has set new benchmarks in many NLP benchmarks by pre-training on large corpora and fine-tuning on specific tasks. NLP's application in cybersecurity is vast and growing. One significant application is in threat intelligence, where NLP algorithms analyze unstructured data from various sources such as social media, forums, and blogs to identify emerging threats and vulnerabilities. For instance, by employing sentiment analysis, cybersecurity professionals can detect negative sentiments or discussions related to potential cyber attacks, allowing for proactive measures. Moreover, NLP enhances the efficiency of security information and event management systems. SIEM systems aggregate and analyze security logs from various sources to detect anomalies and potential threats. By incorporating NLP, these systems can process natural language logs, extracting valuable information and identifying patterns indicative of malicious activity. For example, NLP can identify specific keywords or phrases associated with phishing attempts, ransomware, or data breaches, enabling quicker and more accurate threat detection. NLP also plays a crucial role in automating incident response. Traditional incident response processes are often manual and time-consuming, involving the analysis of large volumes of data to identify the scope and impact of an attack. NLP-powered systems can automate these processes by extracting relevant information from incident reports, correlating data from multiple sources, and generating actionable insights. This not only reduces the response time, but also improves the accuracy and effectiveness of incident handling. Despite its numerous advantages, NLP in cybersecurity also faces several challenges. One significant challenge is the ambiguity and variability of natural language. Different individuals may use different terms to describe the same concept, making it difficult for NLP algorithms to accurately interpret and categorize the data. Additionally, the presence of noise, such as misspellings, abbreviations, and slang, further complicates the processing of natural language. Another challenge is the need for large annotated datasets for training NLP models. Annotating data is a labor-intensive and time-consuming process, requiring domain expertise to ensure accuracy and relevance. Moreover, the rapidly evolving nature of cybersecurity threats necessitates continuous updates and retraining of NLP models to maintain their effectiveness. Privacy concerns also pose a challenge in the application of NLP in cybersecurity. Analyzing large volumes of text data, particularly from social media and communication channels, raises ethical and legal considerations regarding user privacy and data protection. Striking a balance between leveraging NLP for cybersecurity and respecting individual privacy rights is essential to ensure responsible and ethical use of this technology. In conclusion, natural language processing is a cornerstone of AI with significant implications for enhancing cybersecurity. The evolution of NLP, from simple models like bag of words to advanced deep learning architectures like transformers, has opened new avenues for analyzing and understanding natural language data. By leveraging NLP, cybersecurity professionals can gain valuable insights from unstructured data, improve threat detection, and automate incident response processes. However, addressing the challenges of language ambiguity, data annotation, and privacy concerns is crucial for realizing the full potential of NLP in cybersecurity. As the field of AI continues to advance, the integration of NLP in cybersecurity will undoubtedly play a pivotal role in safeguarding digital assets and mitigating emerging threats.